So I have an interesting problem. I think you might find this useful for your practice, especially if you are designing bridge elements. I'm going to be applying my 8-step solution and see what type of checks needed, what are the critical aspects. I'm going to give you a couple of tips which are also applicable to other types of problems. All right, let's get into it. Before we get started, please don't forget to subscribe to this channel and like the video. What I'm going to be solving today is a wall. It's 16 feet tall, 3 feet wide. So I'm showing you both front as well as side view. Very significant load applied, which is 3000 kips. There is a bearing plate with dimensions given. Concrete strength 4 KSI, FY, again regular strength reinforcing steel. We are going to be doing the reinforcement design based on AASHTO LRFD 9 edition. I selected this problem because it's a little bit interesting, very heavy load, so this might require 2 separate strut-and-tie models, because if you look at the front view, you are going to be having spread of stress to occupy this 12 feet wall section. If you look at the side of it, it's again going to spread to occupy 3 feet section of the wall. This is showing an enlarged version of the same wall. I'm going to be developing 2 separate strut-and-tie models, one for this 12 feet section, the other one is for through thickness. We don't do this usually. It may not be needed in many cases, but because the load is very significant, let's look at that. It may not govern, it may not be an important aspect, but it might be for this particular question. So 8-step solution, that's how I solve strut-and-tie models. The first step would be the developing the truss model and solving for member forces. Of course, this is a very critical step. For any model, you would need to determine a top chord, which could be strut or a tie, which we don't know it yet. We need to identify the disturbed region. Disturbed region, by definition, we are looking at h away from the load application point. If this is 12 feet, the disturbed region is going to be again 12 feet, 1-to-1 aspect ratio. There is going to be spreading of stresses. If you have no disturbed region, stress will flow right away without any change of trajectories. But if you have this discrepancy between the width of the section different than the load application point, which is bearing plate in this case, you are going to be having a disturbed region which is going to be the same as this B distance. So that's the disturbed region. After that, stress would be occupying the entire section. My solution would also follow this basic principle. This is the first step in any strut-and-tie analysis. Of course, in real life, we distribute that reinforcement through the disturbed region. Of course, you can always concentrate it in a band, but in my solution, I'm going to be using the entire disturbed region to distribute that reinforcement. Of course, we are going to be putting crack control reinforcement. We are going to be checking anchorage as well as additional code requirements. For this example, what I would like to do is to put my tie at the centroid. So this is going to be 6 feet or 72 inches. Very important assumption which I have to make is the distance of the top strut from the top of the section. If you select this to be too narrow, it may not pass. If you make it too large, it's going to reduce the angle. It's going to be an issue. In my first attempt, I selected 3 inches. So in this solution, I'm going to be taking this as 3.5 inches. This should pass. If you want to take it as 4 inches, that should be fine as well. Of course, we are going to be checking that dimension. The other important aspect in any strut-and-tie model, if you have a load applied to a location and if it is spreading, you want to separate that load to create 2 different nodes. This makes the model more efficient, it makes it more realistic, as well as it makes checking easier because you separate it into multiple nodes. For this one, because I'm going to be spreading it into 2, it does make sense to spread this into 2, 1500 in terms of forces. What I need to do is to divide the distance into 4, which would give me 9 inches. So 9, another 9, another 9. I'm going to be sending my compression, so this is going to be going to that node. So this is the initiation of the stress. At the bottom of it, again, let's just sketch the center line, which is going to be, I'm going to divide it into two, so it's going to have 4 different segments, 1500. At the end of a disturbed region, the stress needs to occupy the entire width, which is what I'm doing in my solution. This is going to this node, this would go to that node. There is going to be the critical tie in between. This is the end of disturbed region. Let's identify this clearly. This strut will go all the way. You will see this is 3 feet or 36 inches, 36 inches, and so on. Perhaps the most critical element would be CD. Name this one as AB. So that is pretty much it. Very basic model. So let's get this checked, see how it would work out. So I'm going to be looking at compressive stress flow across 12 feet wall length. I need to do a truss analysis, of course, to get this problem started. If this is 1500, this truss, this would have 1500. I'm only solving half of it because it's a symmetrical system. I need to determine this as well as angle. Angle is, as you know, it's super important. Larger the angle, the more efficient the model will be. Horizontal strut force, which is pretty important. 1500 times 36 minus 9 inches is going to give me the horizontal distance. So 36 inches minus 9. In terms of vertical distance, 72 inches minus 3.5. In other words, what am I calculating is this. So I'm calling this distance, that is vertical, and this one horizontal. 591 kips. Resultant force would be 1612. So 591 is this one. And resultant force, I'm just writing it here. The horizontal component 591. Based on that, the tension in the tie needs to be 591 kips. So I would also like to do a similar calculation for the thickness. Also check through thickness. So let's look at that. Again, I'm going to be dividing the load into two. So my disturbed region would be 36 inches or 18. Same assumption applies. The distance from the top would be 3.5 inches. If you prefer 4 inches, that's fine. You can use it as well. Let's show the tension in this location. We are dividing the force into two because it's spreading into two. In terms of distances, 7 inches, 7, 7, and 7. There is going to be a uniform stress once, and of course what we are interested would be the resultant EFGH. So this is 1500. What I'm looking for is this horizontal component because this is 36. This is center line. These are going to be 9 inches. 18 minus 3.5. So based on this, 207 kips. Low number based on super good angle. Theta 68.5 degree, which is a very good angle. For the other one, it comes out to be, I'm just calling it theta again, that's the common notation, 82.1 degree, which is very good. Resultant force will come out to be 1514. So the horizontal component 207, the resultant minus 15. That concludes the first step, which is developing the strut model. Step number 2 is to look at what is needed in terms of reinforcement. These are my standard steps. Any strut-and-tie question, I solve it using these steps. So we are going to be looking at two ties, CD with this force as well as GH with 207. The general formula is AS should be larger than tension divided by phi S times Fy. So tension 591 kips. AASHTO uses reinforcing steel multiplier as 0.6. If you are using a different code, you can adjust that. Otherwise, it's going to be the identical solution. If pairs of number 6, these are US number 6, are used, each number 6 would have 0.44 square inch area. So what I'm going to be doing, 10.9 divided by, we are using two layers, one at each face, 2 times 0.44, 0.4 pairs would be needed. The distribution will use the entire disturbed region, so I'm going to be using in my solution 12 feet distance. 2 layers of number 6 separated at 11 inches. Let's look at GH. So for this one, required area is 207 kips divided by 0.9 times 60, and that's going to give, of course, much smaller, but it's going to give some area. So this is what we need to provide. If pairs of number 6 are used, 3.83 divided by 2 times 0.44, 4.4 pairs. I'm going to be distributing this over the entire disturbed region, which is going to be 36 inches. 2 layers, number 6, 8 inches. It's more frequent. It's more than your main reinforcement because we are distributing it within a short distance. That's pretty much it. In a strut-and-tie design, you finish the design at the very beginning. Of course, the strut-and-tie method requires checking 4 different aspects. What are those? We need to check ties, which is done already because these are the tie check. I put the reinforcement to satisfy tie strength requirements. It's done already. 3 more to go. We need to check struts. We need to check nodal zones, as well as we need to check anchorage. So let's start with the nodal zones. Nodal zone check includes the nodal zone itself, which also incorporates the horizontal struts or ties as well as vertical struts and ties. So step 3, as I'm doing it, will involve horizontal and vertical members only. Step 4 would be dedicated to diagonal members. Step number 3, of course, also involves bearing check. So I'm going to be checking whether the bearing area is sufficient to resist 3000 kips. I'm going to be starting with global bearing check, 36 by 28. The node type at that location is compression, 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 CCC, and based on AASHTO CCC multiplier is 0.85. BR, which is the strength of the nodal zone, is going to be phi C, which is 0.7 times 0.85 F prime C, which is 4 KSI, times plate area, which is 36 inches by 28 inches. If you are looking for more explanation, 0.85 is CCC limit, 4 KSI F prime C. This is the area bearing plate. So if you do this, it is not going to pass 3000 K, not good. So what I'm going to be doing is to incorporate confinement modification factor because I have some available space. If you look at AASHTO, there's a provision which lets you use the unused concrete because if you have additional concrete around the bearing plate, it confines it, so you can benefit from that. Not a lot. If you look 28 inches, so I have 4 inches from both sides that I can use. So I'm going to be looking at confinement modification factor. This factor is used in Canadian code, it's used in AASHTO, it's used in ACI, it's used in Euro code. It's pretty much the same. Typically it's shown with small m. Area 2 is enlarged area. The original area was 28, but we are permitted to add 2 times 4 inches. That's the available area. And I'm permitted to add the same to the other dimension as well. Enlarged dimensions should be proportional. The original area, which is called is A1, is 28 by 36. So what is M, which is 1584 divided by the original area? You have to take square root of this, and the result should be less than 2. 2 is the cap. You cannot exceed that number. So we got 25% additional capacity. I'm just checking it again. BR, it's going to be 1.254 times 2399. It's going to be just enough. So it's a pretty tight design. So then if you start tight, expect issues to come up in the further checks. I don't include confinement modification factor from the beginning because it's additional effort. Don't include it, check it. If it passes, that's fine. You don't have to worry about this calculation. I only consider it if it fails. If it fails, you can turn to this confinement modification factor and try to get some additional capacity. So I'm going to show you a page from my lecture notes. If you look at confinement modification factor, you have the bearing plate. You can consider confinement by concrete around the bearing plate. This is the formulation. So A2 divided by A1, upper limit is this one. So the areas should be proportional. So now I'm going to be checking nodal zones. We have two nodes to check. We have node A. Also, we have node C. Node A, as I mentioned before, it is CCC type node with 0.85 multiplier. Node C is CCT type node with 0.70 multiplier. PR, it's going to be phi C times 0.85 F prime C. So here, what I'm checking is node A. I'm checking strut AB because, as I told you, in this check, involves checking horizontal and vertical members only. So there is really no vertical member. The only thing to check would be strut AB. In terms of strut width, it's going to be 3.5 times 2. In terms of other dimension, it's going to be 36 inches. Phi C, this is strut AB area. The force which we have 591, which is again very tight. In my first solution, I used 3 inches, it didn't pass, so 3.5 is the minimum that would make this model pass. It is done. So I'm done with node A. There is really nothing else to check. Now I'm looking at node C. There are two things to check. I'm going to be checking tie CD as well as the vertical one. Again, node C is CCT type of a node. Limit would be 0.70 F prime C. Let's check the tension, which is TR. I'm checking whether there is enough concrete for the tension, which shouldn't be an issue because this is at the mid section. You know, you have a lot of distance, so this you can omit this check. But let's check that with some numbers. This is again phi C 0.7 times 4 KSI. In terms of the thickness, there is, a lot. Even you use 12 inches, which is a random number, there is more than that, which is 847 kips. So even if you have 12 inches, which is 6 inch above, 6 inch below, it's going to make this pass easily. 591 kips. So this check is definitely, you should omit this. I want to be complete and show you what's involved. The other one is checking the strut. It's going to be the same limit, except the area would be changing. So if you look at that strut, the width is significant, very large number, so 36 times 2, and depth is again 36 inches, and it's going to give a huge number. So there is absolutely no problem with that. So these two checks, really, you can omit these. I'm going to repeat the same with 3 feet wall thickness. Node E, that's going to be the critical node to check. Stress limit is the same, CCC 0.85 F prime C. What I'm checking, strut EF, compressive capacity 0.70 times 0.85 for KSI. Again, 2 times 3.5 inches times 144. 12 times 12 is 144. So that's the thickness, 2399 kips. But what we have is 207. Node G, it would pass with no issues, so I'm not going to check that. Step number 3 is completed. Couple more checks. Diagonal strut capacities tend to be critical, so let's look at this. Again, I'm going to be doing this check twice. I need to check strut AC for the original front view model, and then through thickness model I'm going to check strut EG. Based on the latest version of AASHTO, there is a concrete efficiency factor which I'm going to be calculating, which applies to both ends. So it would apply node A as well as C. Let's start checking node A. Concrete efficiency factor is 0.85 minus 4 KSI, which is F prime C divided by 20. 20 is a constant part of the equation. This number cannot exceed 0.65, which is the upper limit. It has to be smaller or equal, so this is the maximum. I need to determine the width of the diagonal strut. Widths of horizontal or vertical struts are relatively straightforward, but diagonal struts you need to use some handouts, which I also distribute in my classes. Here the situation is this one. So you have the load applied from the top, you have a horizontal compressive strut, this is a diagonal strut. So this is exactly what I'm trying to determine is this one. So the width of this strut going into node A, which is exactly this width, which is LB, in my case 18 inches, times sine theta, which we found it to be this angle, plus HS. HS is the total width of the horizontal strut, which is 3.5 times 2 times cosine theta. 18 inches, which is 9 times 2 times sine theta, plus 2 times 3.5 inches times cosine theta. So if we do this, width will come out to be 19.3 inches. We got the efficiency factor as well, and we are ready to proceed with PR, which is going to be again phi c times limit, which is 0.65 for KSI area. Thickness 36 inches. Based on this, we are extremely close. No, it fails. 64. Diagonal struts are critical. Typically, it's really common to get failure. It's not good. Yeah, 28% overloaded. So definitely there are multiple solutions for this. You see the equation, you see what's input into the equation. You might increase concrete strength. That would enhance your design overall. You might increase the thickness of the section. That's another one. If you don't want to change these, bearing plate would be the one. My solution would be increase bearing plate size. It was too tight to begin with. Remember, we had to use confinement modification factor. So I think for this situation, the first solution attempt should be increase size to 42 inches. So it was 36. Once you increase the plate, the nodal geometry will change. So you need to redo this example. It's really a good idea to also solve it yourself, because it always looks like you understand the solution looking at somebody else's solving it, but good idea to solve it yourself to better understand. Once you increase the bearing plate dimension, it's going to help the model also overall. It's going to improve the theta. It should reduce the forces. So what reinforcement we selected in the previous step should be more than enough after increasing the bearing plate size. So I'm going to proceed. I'm not going to change the design. So you want to get some practice, that would be a good practice. You change the bearing plate size to 42. The other node to check would be node C. I'm not going to check it because it's going to pass for sure. Node A is failing because of a super narrow strut width. This would have very large strut width. It could have, because there is concrete available. It shouldn't have any problem passing it because force is the same, multipliers, all of them including concrete efficiency factor the same, so that should pass without any difficulty. So let's see the true thickness, 3 feet wall thickness, whether this would pass or not, which is EG, strut EG. Again, the critical node would be at node A because I only have 14 inches of bearing plate to use. Remember, I didn't change the other dimension of the bearing plates. Same 28 inches. There is really not a lot of distance to increase it. Let's see whether this would pass. If it doesn't, we have to think about what to do for this check. Concrete efficiency factor do not change. It's one factor for the entire problem because it's only function of F prime C. Strut width would be, again, this is 14 inches times sine theta is 82.1, and then plus 2 times 3.5 inches times cosine 82.1. So if 14.8 inches, PR would be 654 KSI. Again, 144 goes into that, so no problem. So there is no problem with this true thickness model, 15-14 kips, so which is much larger, which is okay. Next step would be to check tie anchorage. There are 2 ties that we need to check. The tie CD, which is across 12 feet wall length, I think this check will not be an issue. This is the strut width, and we need to check it starting from this edge. So I'm going to be check whether straight bars are sufficient or whether there is any need for the hook. So the available length, definitely you have at least 36 inches. There is going to be some more. I didn't calculate this width. I'm going to check this with 36 inches. Even that might pass. If it passes, there is no need to calculate this any further. LD available, which is going to be 36 inches plus some distance based on strut width. We need to look at development length for the bar which I'm using, which is number 6. So straight bar development length required for this bar is 35 inches. So even without considering the strut width, I don't need a hook. No hook needed. Let's look at the development length for 3 feet wall thickness, which is tie GH. I'm going to be using closed stirrups or ties for that location, which is going to be fully developed. So I have some sketches. I use these in my classes for additional modeling. In this example, I am not going to need those. Step number 6 is a typical step. Provide crack control reinforcement, which is extremely important. That enables a deep member to resist loads, both in the ultimate as well as serviceability limit states. Let's use 2 layers of number 6. AASHTO requires 0.3% crack control reinforcement. Both horizontal and vertical will be the same. 2 legs, because I have 2 layers, 44 square inch, 1 bar area. 36 is section thickness times spacing, make it equal to 0.3%. So vertical spacing will come out to be the same as horizontal spacing. It's going to be 8 inches. Crack control reinforcement is typically large based on AASHTO requirements. So if you look at the solution, tie CD, we were using number 6 at 11. Crack control will govern it. So crack control, 2 layers, number 6 at 8 inches. This is same as crack controls. Note, this is larger than tie CD reinforcement and thus will govern. So that's what we are going to be using for this reinforcement. For certain members, there are certain requirements. If you have those requirements applicable to the specific problem that you are solving, then this is the step I use for applying those requirements. This is a specific type of system which AASHTO includes some provisions. AASHTO requires bursting reinforcement because this is the bursting force we calculated. The true thickness model is important because it can burst the section if you don't have that reinforcement, and AASHTO calls this as a bursting reinforcement. So we have that already, so we don't need to do anything additional, but let's summarize it here. So tie GH provides bursting reinforcement. You can see AASHTO article 59565B, which requires spirals, closed hoops, or anchored transverse ties. So I'm going to say closed hoops because that's what I'm using. And also other requirements, maximum spacing. AASHTO do not like further than a certain spacing, which is 12 inches, which we are good, 8 inches, or 24 times bar diameter, dB, for which we are in a good shape. The other requirement for this special case is called spalling reinforcement. This is like an anchorage zone. You are resisting significant compressive forces, and there could be spalling on the top surface. I'm going to show you a handout which I distribute in my classes. This is from Professor Collins and Mitchell, Prestressed Concrete Structures, University of Toronto. There is a significant force applied and you might have spalling at the top surface, and this is coming from elastic stress analysis, and you can see 0.17, which is 17%. Of course, it depends on the proportions, how narrow the plate as compared to the section, or how wide the plate as compared to the section. So as a general rule of thumb, 2% of the force applied is used as spalling reinforcement. You can see different cases in this handout. AASHTO recognizes this and requires 2% of the concentrated force on top surface. So based on this, a spalling would be 2%. Call this P ultimate. It's a factored load divided by twice SFY. So if we do that, total force 3000 kips, 60 ksi, 1.11 square inch. Provide two layers, number 7 near the top surface. Same clause also recommends reinforcement to the edge. So I'm going to say also provide two number 7 as edge tension reinforcement. These are special requirements. Usually we don't have special requirements for typical members, but this is a little bit specialty type of member with heavy concentrated load. That is pretty much it. Details really important, so I would like to show these carefully on my final. Spalling reinforcement will be at the very top as I showed you. We want development, so I'm going to be hooking this 90 degree. This has nothing to do with the strut-and-tie model. This is a code requirement, so this one is number 7 at each face. What this is, spalling reinforcement. Edge reinforcement will be at the edge. It would be a good idea to also use a 90 degree hook, provide continuity at the top surface, which is a really critical location because the force is introduced at the top. This is number 7 at each face. And what this is, edge tension reinforcement. Again, this is not something we calculated in the strut-and-tie model. This is an additional AASHTO requirement. This is that again, and also we are not designing foundations. The system has foundation. That's for some other video. I'm just showing you the wall design, and I want to show you the same reinforcement in the other view, so it would show up. The legs will show up. Tie GH bursting reinforcement. This is coming from strut-and-tie. 1, 2, 3, 5 would fit within 3 feet distance. I should say 5. So the same reinforcement really shows up. What this is, let's sketch it here. Number 6 hooks. The final addition would be crack control reinforcement, which is going to act as if it was the main reinforcement because it governed it. It's going to be covering the entire section. You want to hook this inside, so I'm just showing you those hooks, and also it's a good idea to show it here. Crack control reinforcement, it's going to be extending from one side to other one, hooked inside. So I'm just showing 2 dots to indicate it goes inside through the thickness. The other one would be probably it's going to be extended into the foundation, which I'm not showing in this. Would like to hook this again, 90 degree hook through the thickness, send it inside. This is going to occupy the entire section width. In terms of how it looks, it's going to be probably one hook, the other end would be to foundation. So pretty well done. That's pretty much it from me today, everyone. Thanks very much for your attention.